Now it's time to begin our tutorial 2. At the beginning, I will introduce myself again and for the last time. I'm Ling Rui and you can call me Ray. If you have any questions, please contact me by sending me emails. If you like to talk to me face to face, you can come to my office. But before you come, please send me an email to tell me when will you come and what question you have. Today's tutorial questions are set by Liu Chang. So if you have any questions, you can contact him for help as well. Now we are going to see what we are going to learn today. Today we have 6 questions, and because time is limited, I will only focus on question 1, 2, and question 6. For questions 3, 4, and 5, you should take them as exercise, and please check the answers after I post the tutorials on Moodle. I will post it around 2 o'clock this PM. Because time is limited, and I will list the frequently asked questions in the slides, so you can see whether you have the same questions. And if you have the questions that I have not talked about during the tutorial, please contact me after the tutorial. And again, I have to stress that it is necessary for you to check the details of Gaussian elimination after the tutorial. Now we begin with question 1. For question 1, the problem is solve the system of linear equation in augmented matrix form. For this question, we have 3 key points. First, I want you to know what is augmented matrix form, then how to do Gaussian elimination, and third, what is reduced row echelon form. The abbreviation of the concept is RREF. Now we go to the solution directly. The first step is to build the augmented matrix as the question asked. Please see the yellow block. It says the augmented matrix is formed by 2 parts. The first part is the coefficients on the left, and the second part is the results on the right. For the coefficient parts, it's actually the coefficients before the corresponding variables. For the first column, the entries is actually the coefficients before the variable x1. There are 2, 3, 1. And then we move to the second column. The entries are actually the variables before x2. There are 1, 2, 3. And for the last column, the entries are actually the coefficients before x3. They are 1, 4, and 0. Now I think you already know how to build the coefficient part of the augmented matrix. Then we move to the right part. For the right part, the entries are actually the results on the right of the equations. So they are 8, 24, and -1. So for step 1, we build the augmented matrix first, and we can build it directly according to the linear system equation. It's very easy. And then we move to step 2. For step 2 is the key point of question 1. I want you to know what is Gaussian elimination. And you can see on this page, we have 2 blocks. One is green and one is yellow. For the green one, they are the frequently asked questions from your classmates. So you can see whether you have the same questions as them. And in the yellow block, I listed the 3 basic operations we need for Gaussian elimination. And now we are going to see what they are. So we begin with the augmented matrix that we get from the first step. For the sake of simplicity, I denote this matrix as matrix 1, and this is matrix 2. We can see from the first step to the second step for Gaussian elimination, the first row of the matrix 1 now become the second row of matrix 2. And the second row of matrix 1 now become the third row of matrix 2. And then we see the last row. The last row in matrix 1 now become the first row of matrix 2. We can see we compare matrix 1 and matrix 2. We just change the positions of the rows. And this is the operation mentioned in the first point. We change the position of two equations. In other words, we change the position of the rows in the augmented matrix. You can see the third question in the blue block. The student asks, from step 1 to step 2, we can change the order of the rows in any way we like. The answer is yes. Actually, you can change the position of the rows in any way you like. But please make an observation for the first column. We can see that the entries of the first column is arranged from the smallest to the largest. Though you can change the positions in the way you like, I suggest you to change the positions to make the entries in the first column to be arranged from the smallest to the largest. By doing this, it will be easier to do the following steps. Now we keep going. This is step 2, this is step 3, and you already seen there are notations below and above the arrow. Now we focus on the notation above the arrow first. It is R2 minus 2 times R1. That means we take the second row of the matrix 2. It's 2, 1, 1, 8 minus 2 times the first row of the second matrix is 1, 3, 0, minus 1. Then we get 2 minus 2, 1 minus 6, 1 minus 0, and 8 add 2. By doing the calculation, we can get the second row here. And now we move to the notations below the arrow. And it is R3 minus 3 times R1. That means we take the third row of the second matrix is 3, 2, 4, 24 minus 3 times the first row of the second matrix is 1, 3, 0, minus 1. And we can get 3 minus 3, 2 minus 9, 4 minus 0, and 24 add 3. Then we can get the new third row of the matrix 3. And you can see after step 2, step 1 to step 2, step 2 to step 3, we make the first column looks like this. Element 1 here is the only non-zero element in this column, and the other elements are all 0. Now we keep doing Gaussian elimination. And this is matrix 3. This is matrix 4. The notations above the arrow is R2 divided minus 5. I think this calculation is quite easy, so please see these elements directly. These two elements. You can see that the element minus 5 on the diagonal now becomes 1. So on the diagonal, we already have 2 element 1. Now we keep going. This is matrix 4. This is matrix 5. And the notation above the arrow now is R3 adds 7 times R2. That means we take the third row of matrix 4 is 0 minus 7, 4, 27 to add 7 times the second row of matrix 4 is 0, 1, minus 1 over 5, and minus 2. After the calculation, we can get the new third row of matrix 5. And you can see after we do the step 4 to step 5, the bottom corner, the left bottom corner of the augmented matrix Now all becomes 0. And we keep going. This is matrix 5. This is matrix 6. And the notation here is R3 divided by 13 over 5. This calculation is easy again, and please focus on these two elements. Now the element 13 over 5 becomes element 1. Now we can see all the elements on the diagonal are 1, and the bottom left corner elements are all 0. Now this matrix looks kind of special, but we will keep doing Gaussian elimination. This is matrix 6. This is matrix 7. And on this arrow, the notation is R2 at 1 over 5 times R3. So we take the second row of matrix 6 is 0, 1, minus 1 over 5 minus 2 to add 1 over 5 times the third row of matrix 6 is 0, 0, 1, 5. After the calculation, we get a new second row of matrix 7. And you can observe that on the left side of the augmented matrix, the element 1 here is the only non-zero element in the second row. Now, there is only one step left. This is the matrix 7, this is the matrix 8. And the last step is R1 minus 3 times R2. That means we take the first row of matrix 7 is 1, 3, 0, minus 1 to minus 3 times the second row of matrix 7 is 0, 1, 0, minus 1. And after the calculation, we can get the new first row of matrix 8. Now, the matrix looks more special. This is the left side of the coefficient of the augmented matrix, and we can see now it is an identity matrix. We only have element 1 on the diagonal, and for the left bottom corner, all the elements are 0. This matrix is special, right? And this matrix is called RREF. I will introduce the concept of RREF in the next page. And now we are going to see how we can get the solutions after we get this matrix at the end. I think you still remember that this is the coefficients before corresponding variables, and this is the results at the end of the equation. So we can write down the corresponding linear system equations according to this matrix. This is for the first row, this is the coefficients before variable x1, this is coefficients before x2, this is x3, and this is the results. So we can write down the first equation like this. And for the second row and the third row, we can write down the equations in the same way. And I mark the non-zero coefficients red. You can see the system like this. So we can directly get the answer. x1 equals to 2, and x2 equals to minus 1, and x3 equals to 5. This is quite easy. And now please see the second question in the block. For the first question, I already show you the Gaussian elimination step by step. So I think you can follow the Gaussian elimination. And for the second question, do we have to show notations during our working like R3 at 7 times R2? The answer is it's not necessary. You can omit the notations when you are very familiar with the Gaussian elimination, but I suggest you to do so because writing down the notations will help you to double check your answer and will make your problem solving process very clear. And I see a question on the screen. Do we need to get to the simplified stage before we derive our answer? If the questions ask you to use augmented matrix form and also ask you to use Gaussian elimination, you should get this you should get the RREF matrix at the end first before you get the answer. And now we are going to illustrate the other two operations mentioned in the Gaussian elimination. We take these two as example. So you can see in this notation, we see 2 times R1 and 3 times R1. This is the operation mentioned in the second point. It says multiplication of an equation. In other words, we do the multiplication of the row. And for the notation, we can write it in this way. R2 at -2 times R1 and R3 at -3 times R1. So this is the addition operation. It says additions of two equations, and in other words, addition of two rows. So after we solve question 1 step by step, I think you already know what is augmented matrix and what's the 3 basic operations to do Gaussian elimination. So we move to the next page. In this page, I will introduce you the reduced row echelon form, RREF. First, we see this point. It is in row echelon form. I think this concept is easy to follow and you can understand it intuitively. Please see the white figure here. We mark the non-zero elements blue. You can see here the non-zero elements are all marked blue. And the shape of the blue pattern is echelon. So I think it's easy for you to understand. So now we move to the second point. Every pivot is 1. Please see matrix here. Pivot means the first non-zero element in each row. So for the first row, this is the first non-zero element. So this is the pivot. And we can see its value is 1. And for the second row, this is the first non-zero element, and its value is 1. And for the third row, this is the first non-zero element. So this element is pivot, and its value is 1. So I think the second point is also easy to understand. Now we move to the third point. The pivot is the only non-zero entry in its column. Now we see this matrix again. This is the first column, and this is a pivot. We can see this pivot is the only non-zero element here. And now we move to the second column. And this is the pivot. And we can see this is the only non-zero element. Then we move to the third column. This is the pivot. And we can see this is the only non-zero element. And as for the fourth row, since there is no pivot here, so this point is not satisfied for the fourth column. Now there are 3 properties of RREF matrix. For the first property, it says all rows that contain only zeros are at the bottom of the matrix. Please see the white figure again. We can see these 2 rows are all zeros, so they are at the bottom of the RREF matrix. It's quite easy. And now we see the second point. It says all rows that contains at least 1 non-zero elements are on top of rows that contain only zeros. We can see the blue patterns. These 2 rows contain at least 1 non-zero element. So these 2 rows are above the all zero rows. These 2 properties are easy to understand. And then we move to the third property. For non-zero rows, the first non-zero number from the left is always strictly to the right of the pivot of the row above it. This sentence seems kind of complex, but we can illustrate it by using this matrix very easily. For example, this is the pivot of the first row. This is the pivot of second row. This is the pivot of the first row. we discuss it in three cases. First, we see the first row vs the second row. It is very obvious that the first row is above the second row. So we can see the pivot here is on the right side of the pivot here. And the second case, we discuss the first row vs the third row. We can see first row is above the third row. So the pivot here is also on the right side of pivot here. And the last case is the second row vs the third row. Again, it's obvious that the third row is above the second row is above the third row. So the pivot here is on the right side of the pivot here. Now we know what is RREF and we know its properties. Now we move to the next page. After we solving the question 1, we know what is the augmented matrix and what is RREF and what does each step mean in Gaussian elimination. But some of you still have questions like this. I know what is Gaussian elimination. I know what is RREF, but I don't know how to get RREF by using Gaussian elimination. I think some of you have the same problem, that you don't know how to find the proper operations and do it sequentially to get the RREF at the end from the augmented matrix at the beginning. And for this question, I think if you are patient enough, Gaussian elimination is quite easy and can be done in a fixed process. I found a useful website here, and please check it if you have problems to find the proper operations to do Gaussian elimination. I will post the tutorial slides around 2 p.m. today. After this question, there are also questions like this. What methods should we use in the exam? Can I use other methods? For the first two questions, my answer is here. According to myself, I suggest you to master at least the following two methods. The first is Gaussian elimination, and the second is inverse matrix. And you can choose the methods you like if the question do not have specific requirements. So if the questions tell you to use the augmented matrix and the Gaussian elimination, please follow the questions and do not use the methods you like. And for the third question, some students have the question like, why should we use Gaussian elimination? It seems quite complex. And actually, I cannot illustrate it very clear now. And I think you will know it soon by doing your homework 1. And you will learn the advantage of using Gaussian elimination. That's all for question 1. And now we move to question 2. If you have questions that I have not talked about, please contact me after the tutorials, since time is limited today. And for question 2, we have 3 key points as well. The first is number of solutions, and there are 3 cases. We will talk about it later. And then there are general solutions. For general solutions, you should know how to find the free variables, leading variables, and how to write down the general solutions. Then is the non-trivial solution. This is a new concept to you, and I think you should bear it in mind because you will meet it during exams, or when you are doing your homeworks. Now we move to next page. We focus on question 2b first. For question 2b, the question is solve the following system of linear equations. The process is fixed. First, we build the augmented matrix, and then we use the 3 basic operations for Gaussian elimination: exchange position, multiplication, and addition. And step by step, we get the RREF at the end. And then we write down the corresponding linear system equations, and we get the answer directly. If you want to check the details of Gaussian elimination, please do this after the tutorial. And now we can see there is a green block. Your classmates have questions like this. Can we always make the left side of augmented matrix an identity matrix? I think the student have the question because in question 1, we have the identity matrix at the end, on the left side of the augmented matrix. And this time again, we get an identity matrix at the end of the augmented matrix at the left side. So the student wonder, can we always get the identity matrix? The answer is not always. Now please focus on the number of solutions. I said before there are 3 cases. The first case is no solution, and the second case is infinite solutions. I will talk about these 2 cases in the next page. Now we focus on the third case. The third case is unique solutions. And you can see for question 1 and question 2a, we have unique solutions. So the answer is, if the system of linear equations only have unique solution, then the left side of the RREF matrix will be an identity matrix. That's the answer for this question. And then we move to the next page. In this page, we talk about question 2b, and you can see there are still 2 blocks. For the green blocks are questions from your classmates again. You can see whether you have the same question. If you have, I will tell you step by step. Then please see the yellow block. In the yellow block, we discuss the first 2 cases in number of solutions, and then I will introduce how to find free variables. Then I will tell you what is non-trivial solutions. Now we start by reading the questions. Under what constraints will the following system of linear equations have solutions? Next, please find the solutions. Again, we start from the augmented matrix here, and we do the 3 basic operations of Gaussian elimination, and finally, we get the RREF. Now you can see on the left side of the RREF, this matrix is not identity matrix. That's because this system of linear equations do not have unique solution. So now we discuss about it has no solutions or it has infinite solutions. For the first point, if there is row 0 equals to b, but b does not equals to 0, then there is no solution. So in this case, that means 2 add a is does not equal to 0, and -6 minus 3a does not equal to 0. In this case, this system will not have solutions, and we can get, in this case, a does not equal to -2. And now we move to the second case. Please see this case. Else, if there is free variables, infinite solutions, well, if we want to have solutions, it's obvious that 2 add a must be 0, and -6 minus 3a must be 0. So we can get the answer a equals to -2. You can see here. And there is a question like this. If the bottom row is all 0, why should we write it? And I think these students means these 2 rows are all 0. Why should we keep it? And I think you should pay attention that we should regard the augmented matrix as a whole thing. So this part is all 0, but the corresponding right parts are not necessarily to be 0 before we give a specific value to a. So if we have not decided the value of a is -2, these 2 rows are not necessarily to be all 0. So we cannot delete it directly. But after we decide the value of a, then we can find that the bottom 2 rows are all 0. So we can delete it. and get the RREF matrix like this. Now we are going to see how we get the answer. You can see the first 4 questions in the block area. Most of your classmates have questions like how to get free variables and how to write the general solutions. So please pay attention to it. Now we can see after we decide the value of A, we get the free variables. Now see this part in the yellow block. We are going to read the definition of free variables. The variables whose columns in the RREF contain leading ones are called leading variables. I think you still remember that the left part of the augmented matrix is the coefficients before variables. So the first column is coefficients for x1, then for x2, x3, x4. For the first column, we can see there is a pivot, and this is leading one. So x1 is leading variables. Again, for this column, we can see there is a pivot, and according to the definition, these 2 variables are leading variables. I think it's obviously. And then we focus on column 2 and column 4. We can see there are no pivots. So according to the definition, they are free variables. And now you may still have questions that what's the relationship between the leading variables and the free variables? And can we exchange their positions, or is the way we use to find the leading variables and the free variables correct? So please see this part. After we get the RREF here, again, we can write down the corresponding linear systems. And I marked the non-zero coefficients red again. So you can see here, after solving the equation 2, we can get x3 like minus 2 times x4. And then we solve equation 1, and we can get x1 equals to 3 add x2 minus 7 times x4. And we can see x1, x3 are leading variables, and they can be represented by constant and free variables. To make things clear, I write an answer block here. We can see x1 equals to 3, 3 is a constant, add x2 minus 7 times x4. x2 and x4 are free variables. Then for x2, we can find the constant is 0, and the coefficients before x4 is 0. That means there is no constraints on x2, and you can set any value. That's very important, any value for x2. Then we move to x3. x3 is the leading variables, and it can be represented like minus 2 is constant, and then x4. And then we move to x4. You can see the constant is 0 again, and the coefficients before x2 is 0. That means there is no constraints on the value of x4. So you can set any value you like to x4. Now we can have a conclusion that leading variables can always be represented by a constant and the free variables, and they cannot change their positions. And again, the way we find the free variables are correct. And we should write answer in a more clear way. And you can see this form is called general solution. So you should, if the question asks you to write down the solutions, you should write it in this way. If this system have infinite solutions. Now, some of you may have questions, how we get the vectors. You can see for the first vector, actually is the constant here. They are 3, 0, minus 2, 0. And then for this vector, actually they are the coefficients before free variables x2. They are 1, 1, 0, 0. And for this vector, actually, they are the coefficients before variable x4. And x4 is a free variable. They are -7, 0, -2, 1. So now I think you already know how to get the vectors in the general solution. And some students also have question. Is the general solution representation unique? And the answer is no. You can see the representation with a green circle. Both the representations are correct, and you can see the relationships between the vectors. We can see this vector times -1 can get this vector, and this vector times -1 can get the vector here. So we have more than one way to write the general solution, and the key point is here. Keep the inner relationship in the vectors. Let's say you can see 7 and 2 are both negative. So here, that means they have the same sign. So here, both of them are negative. And after time -1, both of them are positive. And we can see one here have different signs from 2 and 7. So here, these two are negative number, and one here is positive. And here, these two elements are positive, and one here is with a negative sign. So it's very important to remember that there is more than one way to write down the general solution, but you should always keep the inner relationship in the vectors. And that's all. We keep going to introduce the non-trivial solution. First, we go through the definition. If all elements in the solutions are 0, the solutions are considered trivial, and non-zero solutions or examples are considered non-trivial. I just use an example to illustrate to you. Please see the small yellow block. We have a very simple equation like this. We have two variables, x1 and x2. x2 equals to 5 times x1. So it's very easy for us to get a solution like this. x1 equals to 0 and x2 equals to 0. So all the elements in this solution are 0. All zeros. And according to the definition, you can see they are trivial solution. And trivial here means they are not important. Not important. And then we continue the definition. We can get a very easy solution here. x1 equals to 1 and x2 equals to 5. And at least one of them are not 0. So according to the definition, non-zero solutions or examples are considered non-trivial. So they are non-trivial solutions. So I think you have learned how to judge if a solution is trivial or if the solution is not trivial. It's a very important concept. You should bear it in mind because you may meet it when you are doing your homework or taking exams. Now we finished question 2. For question 2, I think you already know how to find the free variables, how to find the leading variables, and how to represent the leading variables with free variables, and to write down the general solutions. And you should also know the general solutions has more than one representations. The key point is to keep the inner relationships. I see. Now we move to next page. After we solve the question 2, some of you still have questions that if a system of linear equations has general solutions, it has infinite solutions. General solutions looks like this, and infinite solutions. The answer is yes, because I said before, alpha and beta, can be any value. So there are infinite combinations of these two variables. So these two concepts are equivalent. And some of you have questions like, is alpha here x2? Is alpha here? Is beta here x4? The answer is yes. Actually, you can understand the representation in this way, but in most cases, I suggest you to use notations like alpha, beta, and gamma instead of use x2 and x4. But if you write x2 and x4, your answer is still right, and you can get marks in your homework or exams. But I suggest you to use notations alpha, beta, or gamma. That's all for question 2. And as I said before, question 3, question 4, and question 5 are exercise for you, and you can do it yourself, then check the answers after I put the slides on the Moodle. Now we go to question 6, the final questions we have today. And for question 6, we talked about 3 new concepts: linear combinations, linear independence, and linear dependence. Please see the example here. We have 3 vectors. And we have a new vector v here. The new vector v is obtained by use 1 times x1, 1 times x2, and 1 times x3, and add them together and get the vector here. According to the definition, in this case, x1 equals to 1, and x2 equals to 1, and x3 equals to 1. And in this case, we say the vector v here is the linear combination by x1, x2, and x3. I think this concept is easy to follow. Then we move to the second yellow block. We talk about linear independence and dependence. Now we go through the definitions first. It says, if there is a non-trivial linear combination such that 0 equals to the sum of lambda I xi, the I from I to k with at least 1 lambda I, and lambda I does not equal to 0, then the vectors are linear dependent. Otherwise, they are linear independent. Before we talk about independent or dependent, some of you may have questions about this sentence. What is non-trivial linear combinations? Again, we take this as example. In this case, lambda 1, lambda 2, and lambda 3, at least one of them are not 0. And I think you still remember how to judge a solution is trivial or non-trivial. So it's obvious this solution is non-trivial since at least one of them are not 0. So this is called non-trivial linear combination. So what is a trivial linear combination? Please see this yellow block. We can see lambda 1, lambda 2, lambda 3 here are all 0. All the elements are 0. All 0. So according to the trivial, non-trivial definition, they are trivial. So they are trivial linear combinations. I think it's easy to follow. And then we move to the independent and dependent. So there are 2 examples. For the first example, actually we want to know whether there are lambdas that satisfy lambda 1 times x1 and lambda 2 times x2 and lambda 3 times x4 equals to 0. We can see there is a obvious solution. x1 equals to lambda 1 equals to 1, lambda 2 equals to 1, and lambda 3 equals to -1. So according to the definition, at least one lambda is not 0, so they are linear dependent. And then we move to the second example. For the second example, we want to know whether there exists lambda 1 times x1 and lambda 2 times x2 and lambda 3 times x3 equals to 0. And you can see the answer is no. All the lambda should be 0. Can the equation be satisfied? So they are trivial solution. And according to the definition, x1, 2, 3 are linearly independent. Some of you have questions that whether the 0 at the end can be other values, and the answer is no. According to the definition, when we list the linear equations, the end should always be 0. You cannot use other values, should always be 0. And now we move back to question 6. For question 6, the question wants us to find whether these three vectors are linear dependent or linear independent. So according to the definition, we write down the linear equations, always 0 at the end. So as we have done before, first get the augmented matrix, and then do Gaussian elimination, exchange, multiplication, addition, and then get the RREF at the end. You can see, according to the RREF, the trivial solution is the only solution. So according to the definition, they are linearly independent. And that's all for question 6. And at the end of tutorial today, I will give you a summary. Today we have learned what is augmented matrix form. It is formed by two parts, coefficients part on the left, result part on the right. Then we talk about Gaussian elimination. If you have problems to find the proper operations to get the RREF, please check the website I shared in the slides. And then we talk about reduced row echelon form. You should know the properties of RREF, and you can judge whether a matrix is RREF or not yourself. And then we discuss the solutions. First, we talk about number of solutions. There are 3 cases. First, no solution. Second, infinite solutions. Third, unique solution. And only when the system have unique solutions can we get the RREF at the end with the identity matrix on the left side. And then for general solutions, you should know how to get the free variables, how to find the leading variables, and then you should use the free variables to represent the leading variables. And you can write down the representations of the general solution. The general solution can be written down by more than one ways. And the key point is to keep the inner relationship in the vectors. And then we have know what is the trivial and non-trivial solutions. If all the elements in the solution is 0, then the solution is a trivial solution. That means the solution is not important. On the otherwise, the solution is non-trivial solution. And lastly, we talk about 3 new concepts: linear combination, linear dependence, and linear independence. I think you should bear in mind that the 3 concepts are closely related to the solutions of specific linear system. And for the specific linear system, at the end of the equation, this end should always be 0. That's all for today's tutorial. And since time is limited, if you still have questions that I have not covered during the tutorial, please contact me or Liu Chang after the tutorial. If you have no questions, you can leave Zoom. Again, if you have questions that I have not talked during the tutorial, contact me personally.